Okay. Noah and I did experiment number 7, which is determining the concentration of fulvic acid. The outline represented introduction, and then the procedure outline. Then we're going to do an interpretation of the data, our data charts, calculations, and our conclusion. The purpose of this experiment was to use titration to standardize sodium chloride and define the concentration of fulvic acid. To standardize sodium hydroxide, we used 4 samples of potassium hydrogen phthalate between 0.3 and 0.4 grams. And we added that to 100 milliliters of distilled water and added 2 drops of phenolphthalein to this in a burette. A burette filled with 0.1 molar sodium hydroxide, then added sodium hydroxide to potassium hydrophthalate until it turned pale pink. This is just us adding the
You're married?
the sodium hydroxide to the burette. Used 10 milliliters of acetic acid and distilled water with 2 drops of phenolphthalein, and we put sodium hydroxide in burette for the unknown. And then this was the technique that we used. The first image is just the it was phenolphthalein, and then once we put the sodium hydroxide into the solution, once pink started to appear, then we slowed down the drips so it would drop by drop until the mixture became completely like a pale pink.
Hopefully a little more pale than that. Okay, for our results, for the first part, which was the standardization of sodium hydroxide, what we did was we took the titrant, which in this case was sodium hydroxide, and we added that to an analyte, which was in this case the pure substance of potassium hydrogen phthalate. And we did that until the reaction went to completion, which was really just until the solution turned a pale pink color. And we recorded the amount of sodium hydroxide that it took. Okay, and this is our results table. In the top line you'll see there is the amount between 0.3 and 0.4 grams. We actually tried to get as close to the same number so that we would know like around what number it was going to change depending, so we wouldn't have to take so many samples and things like that. And we started at 0 every time, once again for convenience, so that we could easily convert whatever the sodium hydroxide, whatever the burette read, that was actually the total volume that we used. And then we could use that volume in the calculations to determine the molarity and as well as the deviation. And we'll show that in the next slide. But as you can see, the numbers for the rough were actually pretty rough. So I actually excluded that from the molarity and the deviation for accuracy. And to find the molarity, we actually just took the mass of the potassium hydrogen phthalate and we multiplied that, or actually divided that by the molarity, or the molar mass, and that gave us the moles of the hydrogen phthalate, potassium hydrogen phthalate. And we could actually easily convert that to the moles of sodium hydroxide because it's a 1-to-1 mole ratio. And then we did just divide that by the volume of sodium hydroxide, which actually we converted to liters. And that was easily, the average molarity can easily be found once you find the molarity of the 3 trials. We just added up the molarity we got for the 3 trials and divided by 3. And that gave us our average molarity, which we actually ended up using in the next part of the experiment. And the standard deviation was also simply found. It was just the difference between the average molarity and the molarity we got for each one of the trials. And we found that average as well. The results for the second part of the experiment was, well, the second part was the determination of concentration of an unknown, and in this case it was just a pre-prepared sample of acetic acid. And there you can see, once again, the ratios and things, the mole ratio is 1 to 1, and we added once again the titrant of sodium hydroxide to, in this time though, we added it to acetic acid instead of potassium hydrogen like last time. And once again, till the reaction went to completion, and that's when it turned pink. Again, same technique we used last time. And this is our table. This time the top row is actually going to be a constant 10 mils because we used that same volume of the acetic acid in each part of the experiment. And then we started at 0 once again to find, and then we titrated until it turned pink, and that gave us our volume right away of the sodium hydroxide. And we excluded the rough again. I know that they aren't as off this time, but just for superior accuracy, I guess, that's why we excluded the rough this time. And we could use that volume of sodium hydroxide there to find the molarity. This time it's a little different. We know the molarity of the sodium hydroxide from the previous experiment, and we just used the average molarity, and then we also knew the volume of the sodium hydroxide as well as the volume of the acetic acid that we had, which is a constant 10 in each type of the experiment. And so we used the M1V1 equals M2V2 equation, and that gave us our molarity of 0.1207 molar of acetic acid. And that was just for our rough. Each one of those sample calculations up top was for our rough. And then for the average molarity, we just added up the one for each trial and divided by 3 to give us our average molarity of 0.12 molar acetic acid. And the deviation was once again just the difference between the average and the molarity for each trial. In interpretation, these are the questions. It said if the potassium hydrogen was contaminated with sodium chloride, what would happen? Basically, sodium chloride, it's a salt that would break apart, attracting the chlorine would attract the hydrogen ions, and that deduction of availability of the hydrogen ions in the solution is going to, basically it's going to raise the concentration of the base, which is sodium hydroxide, and lower the concentration of the acid, the potassium hydrogen because of the less hydrogen ions in the solution. And the next question was, why did we standardize it instead of just simply weighing out the sodium hydroxide? Basically, sodium hydroxide is an extremely hygroscopic substance, and if we would have just weighed it out, we would also been weighing the mass of the water as well that it attracted. And potassium hydrogen is a very pure primary standard, and it's going to allow you to have an extremely accurate results. And the last one, if sodium bicarbonate was used like we used the potassium hydrogen in this example, what is basically is saying what will be the molarity of the hydrochloric acid if the reaction occurs, this reaction there. This time, however, we found it by taking they gave us the amount of sodium bicarbonate, so we could simply divide by the molar mass, and that will give us the moles. But this time, it was a 1 to 2 mole ratio, so we ended up having to multiply the moles of sodium bicarbonate by 2 to give us the moles of the hydrochloric acid. And once we did that, it was just simple. We could divide by the liters of hydrochloric acid, and that gave us the molarity of that hydrochloric acid to be 0.1121 molar hydrochloric acid. And there are references.